In this video, I am explaining design of synchronous sequence cycle. So let us consider some design an asynchronous sequence cycle that has two inputs x2 and x1 and one z. When x1 equals 0, the output z is 0. The first change in x2 that occurs while x1 is 1 will cause output z to be 1. The output z remain at 1 till x1 equals to 0. So what is the first step? First step we have to state diagram. To draw this state diagram, let us consider. So this is the input state, initial state. Initial state consists x2, x1. So x2, x1, 0, 0. x2, x1, 0, 0 is equal to 0. Now, there will be chance of 1 will change. So from 0, 0 to 0, 1, 1, 0 change. 0, 1 change means here x1 is 1, but x2 does not change. So output is equal to 0. Now from x1, from this is the 1, 0 change. Now x2 is first change in x2, but x1 is 0. So output is equal to 0. So output is equal to 0. Now from this state, we have to consider two state. One is nothing but 0, 0. Another one is nothing but 1, 1. So when it comes 0, 0, what is the output? X1 is 0, so output is equal to 0. So the state, that means that B state is returns when you are giving input x2, x1 equal to 0, 0, it returns to initial state. Then another one chance of combination is nothing but 1, 1. That means what? Now x1 is 1. Now x2 is first change in x2. First change in x2. So output is equal to 1. So output is equal to 1. So this is the new state. Now from this 1, 0, there is a two possible way of combination. One is nothing but 0, 0. Another one is nothing but 1, 1. When it is 0, 0, it returns to initial state. When it comes 1, 1, so you see now x2 is 1, x1 also 1. So here x1 is 1, but x2, this is not first change in. First change in from the C state itself it came. So the output is equal to 0. So now new states are D and E. So from this D, there is a two possible transition. One is nothing but 0, 1. Another one is nothing but 1, 0. So when it comes 0, 1. So you see here this is the 0, 1. Another one is nothing but 1, 0. So 1, 0 means what? X1 return to 0. So output is equal to 0. So it returns to C state. So here this is 0, 1 state. 0, 1 means what? Here x1 it remains 1. So output is equal to 1. So now it forms the new state. It creates new state which is nothing but F. So F is nothing but what? 0, 1 bar 1. So now from this C, there will be the two possible transition. One is nothing but 0, 0. Another one is nothing but 1, 1. When it is 0, 0, it returns to initial state A. So now here from this C, here 1, 1. So 1, 1 in the sense what? Here x2, x1 is 1, but x2 this is not first changing, so output is equal to 0. So now we are getting the new state which is nothing but E. So now from this E, there will be the two chance of transition. One is nothing but 0, 1, another one is nothing but 1, 0. So now you see here, this is the first change it, 1 to 0. So output is equal to 1. So here, given x1 is 1, this is the first change it, so output is equal to 1. So it returns to F state. So here, from this 1, 1, 1, 0. 1, 0 means what? X1 is 0. So output is equal to 0. So it returns to C state. So like we have to form this state diagram. Now, next the final state is nothing but F. F is nothing but 0, 1. From this 0, 1, there will be two possible transition. One is nothing but 0, 0. Another one is nothing but 1, 1. So when it is 0, 0, it returns to initial state. 1, 1 means x1 is 1. So output it remains 1. So it goes to B state. So now we have to complete this state diagram. So from this state diagram, we have to write the primitive flow table. So how will you write the primitive flow table? So now you see present state is A. After giving input 0, 0, 0, 1, 1, 0, 1, 1. What is the next state we have to write? So after giving input 0, 0, it goes to A state. Output is 0. So we have to write only the stable state output. That means after giving input, next state also present state means that is nothing but we can say as the stable state. We have to write output only for the stable state. Next, when you are giving 0, 1, it goes to B state. When you are giving 0, 1, it goes to B state. What is the corresponding output? 0. So this is the unstable state. So we have to just look back. So 1, 1 transition it is not possible. So we have to put as dash comma dash. Now 8, 1 when you are giving 1, 0, it goes to C state. So C state is unstable state. So we have to write as look back. Now let us consider the B state. So when you are giving 0, 0, it goes to A state. When you are giving 0, 1, it goes to B state. B is the stable state. So we have to write the corresponding output. Then when you are giving 1, 1, it goes to D state. So D is unstable state. So we have to write as don't care. Then this combination is not possible. So don't care command becomes right. So now let us consider the C state. When you are giving 0, 0, it goes to A state. 0, 1, not possible. 1, 0, it goes to C state. This is the stable state. So we have to write the output for the stable state. Then when you are giving 1, 1, it goes to E state. So this is unstable. So we have to write as low. Now consider the D state. So this is the D state. So when you are giving 0, 0, that combination is not possible. So next 0, 1. So here when you are giving 0, 1, it goes to F state. So this is unstable state. So F that we have to write. Then 1, 1, it remains in D state. So this is the stable state. So we have to write the output for this state. Next, when it goes to 1, when you are giving 1, 0, it goes to C state. C is nothing but unstable state. So no need to write the output. So like we have to complete E and F. So this is nothing but we can say as the primitive flow table. So from this primitive flow table, we have to complete the implication table. To reduce the to go for the state reduction, we have to use this implication table. For this, you have to write what are the present state. So A, B, C, D, E. Then here from B to F, we have to write. So first we have to combine A and B. So next state and output are equal means you have to put a tick mark. Then you have to combine A and C, then A and D, A and E, then A and F. If states are not equal, just you put as cross mark. That is, after giving input, next state and output are equal means we can say those two present states are equal, then we have to put a tick mark. If the next state and output are not equal, then you put as cross mark. So this is the implication table. After this implication table, we have to go for the merger graph to get the maximal compatibility pair. So here what are the present states you want to write? A, B, C, D, E, F. So you see here A and B are equal, A and C are equal, C and E are equal, D and F are equal. So like you have to draw the line. So what are the equal states? Just you join those equal states which forms the equal state. Now you see here if AB equal means AC is not equal because C and B is not equal. So you have to consider A and B is equal, C and E is equal, then D and F is equal. So no need to consider this equal state. So this is nothing but we can say as the maximal compatible pair. So from this merger graph, we can get the maximal compatible pair. So here, by equal states are A comma B, C comma E, and D comma F. So from this equal state, next we have to draw the or we have to go for the state assignment. So we have to assign the state, we have to assign the binary values to the states. So let us consider A comma B equal to S naught, S naught equal to 0, 0. Then C comma E equal to S1 which is equal to 0, 1. D comma F equal to S2 which is equal to 1, 0. Then after that we have to write the reduced flow table with state assignment. So we know what is the primitive flow table. So from this primitive flow table we have to write what is the reduced flow table with state assignment. As you know, A and B are equal, then that state is nothing but S naught. We are assigning the binary value is double zero. S1 1 0, S2 S1 0 1, S2 1 0. So after giving input, what is the next state? Next state is A, here B, B is nothing but A, here D, D is nothing but C, C, then here C. So now A is nothing but what? S naught, C is nothing but what? S1, D is nothing but S2. So like we have to complete this reduced flow table with state assignment. Now, you see here, this is S1 is 0, 1, S2 is nothing but 1, 0. So here the 2-bit changes is not possible. That means S1 to S2 transition and S2 to S1 transition is not possible. So that is nothing but we can say as the critical race. To avoid this critical race, we have to use one unused state as the temporary state. Here we haven't used 1 1. So we have to use that 1 1 state as the temporary state. Then we have to draw the transition from S1 to S3, S3 to S2. We have to write the same thing from S2 to S3, S3 to S1. We have to complete. Okay, we have to draw the as we have to complete this state assignment. So like we have to complete the reduced flow table with race-free state assignment. So after including the temporary state, we have to draw or we have to give the flow from S1 to S3, S3 to S2. The same thing from S2 to S1, from S3 to S2 to S3, S3 to S1 we have to write. That is nothing but we can say as the race-free state assignment. After this race-free state assignment, we can go for the transition table. This transition table, we have to write the present states, then what is the next state, comma, out. Right. Then we can go for the KMF for next state and output. So we have to derive KMF for F2 plus and F1 plus. Then just by using present state and external input, we have to derive what is the F2 plus. By using present state and external input, we have to derive what is the F1 plus. Like we have to derive for output Z. So after deriving the expression, finally we have to complete this logic diagram. So in this design procedure, first we have to draw the state diagram. From this state diagram, we have to write the primitive flow table. From this primitive flow table, we have to derive the implication table for state prediction. Next, we can go for the merger graph to get the maximal compatible pair. Then we can go for the race-free or reduced flow table with state assignment. Then we can go for the race-free state assignment. Then we have to write the transition table. Then we can go for the schema for next state and output is that. Then finally we have to complete the logic diagram. So this is the design procedure or design of asynchronous sequences circuit. This is the design of asynchronous sequences circuit. Thank you.